Okay, this is a type 2 problem where we're trying to find flow rate. In a problem like this, there's usually an iteration involved, and the design, meaning the lengths and diameters, are laid out. In this case, we have the design here, spelled out, where you have a pump at point A, pumping fluid to point B through a filter, around a bend, around a second bend, and dumping into a reservoir. The flow is oil, and what we're trying to find is the flow rate coming out of this system into the reservoir. What's given to us is the pressure, the losses or loss factors associated with the filter, the elbow, and then the density and kinematic viscosity of the oil. Where do we start this problem? Think about it for a moment. Okay, so where we start a problem like this is usually with continuity, conservation of mass, or conservation of energy. In this case, we're going to start with conservation of energy. And the trick or the skill that you want to develop is picking the right control volume and being able to justify it and simplify it, or help simplify the problem by picking the right control volume. In this case, we're going to pick a control volume from A to C. So let me draw that. Here's A, here's C. The important part to note with C is that we're going to pick a point just outside the tube, and we're going to assume it's a free stream. In a free stream, pressure at C equals 0 gauge. Now let's apply the rest of the energy equation. PA over gamma plus VA squared over 2G plus ZA plus H of a pump equals PC over gamma VC squared over 2G plus ZC plus H turbine plus HL. And those are the losses associated with it. So where do we go from here? Right away, we're going to try to simplify. PC will go away. As we said, it's in a free jet. Because it's just outside the tube, its diameter is equivalent to the diameter of flow at point A. So therefore, we can assume that VC and VA cancel. There is an elevation difference. There's no turbine, so this goes to 0. And you're given a pressure, PA. We are now going to look for a flow rate, and I should say because we picked A at a point beyond the pump, H of the pump will go away as well. Our next step is to try to reduce it further. How can we do that? We can convert HL into its subcomponents. So HL major is equal to friction factor LdV squared over 2G which can then be simplified to friction factor, the diameter of the pipe, should have told you that before, is ID is 50 millimeters. So as we go back down to that equation, in the denominator, this would be 0.05 meters. If we add all the lengths, 6.5, 4, 10.5, 11, 13 meters in length, times the v squared, which we still don't know, times 2, times 9.81 meters per second squared, and this goes to 13.2518 friction factor v squared. Now, of course, there are bends and turns, so we've got definitely some minor losses. So that's HL minor, and that can be written as a summation of all those losses times the velocity inside the tubing divided by 2g. That is going to be equal to 2.3 plus 3 elbows times 0.9, the loss per elbow. All of this times v squared over 2 times 9.81 meters per second squared, which provides final value of 0.2548 v squared. Each of these solutions can be substituted into this HL term. Okay. If we substitute in to the energy equation, we can write it in the following way. For PA, we can write the 400. It is in kPa, so we've got times 10 to the third newtons per meter squared times the rho of the oil, 890 kilograms per meter cubed, times G, and 0.81 meters per second squared. Velocities have canceled out, so that's 0. We'll assume the datum, or the starting point for elevation, is at point A, so that's a 0. And then finally, we've picked a point just to the right of the pump, so the pump head is not included. So once again, another 0. Say that's equal to the pressure at C, which is again atmospheric. The velocities have canceled out, and there's a 2 meter rise. You went up 4, down 2, so the elevation change is 2 meters, plus the head loss terms, which are 0.2548 plus 13.2518 friction factor, all of that times v squared. Solving for v squared, or I should say v, we have the following equation. So 6.6192 divided by the square root of 0.2548 plus 13.2518 times the friction factor. So in this case, we've got one equation, 2 unknowns. It's not going to be very helpful. What else can we do? Well, let's first identify this as a critical equation. Equation 1. And let's look for another equation. What else could we do, or what other equations could we pull from where we could relate velocity to something important? Well, one way to think about it is that friction factor is a function of Reynolds number and relative roughness. In this case, we're asked to pump it through, once again, a pipe of oil. A typical pipe in this case to pump that is a cast iron pipe. And really at the beginning we should have said that. So we should make a note of that right now. Cast iron pipe. Going back down, if you know that it is cast iron, you can get the relative roughness. You're given the diameter. So this entire element is known. Why don't we just go ahead and calculate it? The relative roughness, E over D, for this type of pipe, and you can look this up in a standard piping table, is 0.26. That's the root mean squared roughness divided by the 50 millimeter ID gives you a relative roughness of 0.0052. That didn't give us an equation though. What's left? Yes, Reynolds number. Let's consider that. Reynolds number equals VD over nu. That's the kinematic viscosity version of it. So that would be V times 0.005 meters divided by the kinematic viscosity that they gave you. And this is it. As you go forward, across, it's now 961.54 times V. This is promised. Yes. Because this friction factor then can be placed in terms of a function of V. Since we know epsilon over D, and we know we can use the Moody diagram. So let's label that as equation 2. Once again, we have two equations, two unknowns, and we're going to go through a standard iteration. So here's what we'll do. We'll label all the key components. Iteration, F assumed, a velocity, and then a Reynolds number, and then a lookup in the Moody. And eventually, the Moody and the assumed should equal. So the first iteration, we'll assume it's a 0.03. We'll use equation 1 to calculate the velocity, and that will be 8.195. The Reynolds number is 788E3. And if you go to the Moody diagram, with this relative roughness, the lookup would be 0.039. And we sense that we're closing in on this problem, and we end up with a new guess. We're taking the F Moody as the new guess, placing it in, just like we did in the previous iteration. We can get these numbers. So that's pretty close. Between the guess, the final, if we take that velocity multiplied by the area of the tube, we can get the flow rate. So the volumetric flow rate equals V times A, which is then 7.3 0.535 meters per second times pi 0.025 meters squared. This is the final result. 0.0148 meters cubed per second, 3.9. Alright, let's get that a little bit clearer, which equals 3.9 gallons per second. In review, what did we do? We started with the clear layout. We went to an energy equation. We sought to select a control volume that helped us simplify, which does take some nuance. We then decoupled or broke down each of the elements of HL major and HL minor. We reduced the energy equation into V equals function of constants and F. We then explored a relationship for friction factor involving relative roughness and Reynolds number. And we went through a classic iterative approach. That iterative approach normally assumes values of friction factor at 0.02 or 0.03 as a practical note. At the end, we were able to calculate the flow rate through the system, and I hope this